This is a part 3 to discuss about aggregates. For this part, we will continue to some of the properties of aggregates, which are bulk density and durability. For bulk density of aggregates, it is the mass of aggregate in a given volume. So you can weight your aggregates, that is the mass, and then divide by the volume, that is the value for bulk density. The good bulk density is between 1450 to 1750 kilogram per meter cubic. And what are the factor affecting bulk density? We have the factor of particle density, particle shape, and then the size, grading aggregates, and also moisture content. Okay, this is a bulk density is used for judging the quality of aggregates. If we have higher bulk density, indicates that there are fewer voids to be filled by sand and cement. For durability, uh, the durability of aggregates or soundness of aggregates is the ability of aggregate to withstand external or internal attacks. So you have aggregates, we need to look to the external attack and also the internal attack. Okay, the soundness of aggregates is the ability to resist excessive changes in volume due to change in environment condition such as freezing and thawing. Okay, this is from external attack. And then alternating wetting and drying. Wetting and drying. Okay, we consider the aggregate is unsound when volume changes result in deterioration of concrete in the form of local scaling to extensive surface cracking. So that is under durability and also bulk density of the aggregates. Of course, we need to test the quality of the aggregates. So the tests include sieve analysis, and then toughness, hardness, and abrasion resistant. So this is second test. Okay, next is soundness, and then absorption, and also specific gravity. So each of these testing is having its own definition. For sieve analysis, you are using a wire mesh to differentiate the size, and we are using mechanical shaker to get the gradation of the aggregates. So we have the size in descending order starting from 75 to 6.3 mm. And then for fine aggregate, we are using the same method, wire mesh and mechanical shaker, but the sieve is smaller. So the sieve is starting from 4.75 to 0.074 mm. So in the lab, you are using that round wire mesh. We have that wire mesh, and we stack this wire mesh, the bigger size at the top and the smaller size at the bottom, and also you have at the bottom the receiving pan. For toughness, hardness, and abrasion resistant, so we need to look into the resistance towards abrasion and impact. So the equipment that used for this testing is Los Angeles abrasion machine. For soundness, it is to look into the resistance to integration underweathering, including heating and cooling in the term of changing of volume. So this is the Los Angeles machine. You put the aggregate inside the machine and will test for the soundness and also the abrasion resistance. So next is the absorption. The absorption determined by measure the increase in weight of oven dry sample immersed in water for 24 hours. So this is your aggregates. Your aggregates, put it into oven, and then after oven dried the aggregates, put it in water, and then we need to measure the aggregate absorb water for 24 hours, then wet at the saturated and surface dry condition. So after oven dried, and then put it in the water for 24 hours. After that, you weight the aggregates. For specific gravity, it is a relative density of a substance defined as the ratio of its mass density to the mass of water. So you have the density of your aggregate, and then divide by the density of water, then you get the value for specific gravity. And this was taken at the temperature pressure of 4 degrees Celsius. Next is to understand the deleterious substance in aggregate. Means that we don't want this material to be included in our concrete mixture. Sometimes your aggregate comes with this deleterious substance if that aggregate is not washed carefully. Deleterious material adversely affect the strength. Definitely will affect the strength, workability, and long-term performance of concretes. That is why this is unwanted material. We don't want this deleterious material. And the total amount deleterious material allowed for concrete mix is about less than 5%. What are the deleterious material? We have impurities, coating, and unsound particle. In terms of impurities, it comes from the form of organic matter, which interfere with hydration of cement. And also, it is consists of decayed vegetable matter in the form of humus and organic loam. And these impurities can be removed by washing the aggregates. Okay, next is the coating. If we have aggregate with coating, it can prevent the development of good bond between aggregate and cement paste. Okay, remember the surface roughness. If your aggregate have some coating at the site, it can affect the bond with cement paste. That coating include clay, silt, and also crusher dust. Why we need a good bond? Because to ensure strength and durability of concrete. Also, to remove this coating is using washing. And the last one is unsound particles. There are two types of unsound particle, which are salt contamination and also unsound particles. For salt contamination, it is caused efflorescent, unsightly white deposit on concrete surface. And after you mix the concrete, you cure the concrete, somehow you see the trace of white material on the top or on the surface of concrete, meaning that in that mixture we have some salt contamination. Salt is deposited on concrete surface, cause corrosion of reinforcement. Okay, inside the reinforced concrete, we do have that steel, and if salt exists in that concrete mix, that still will be corrode. And how to remove that one is by washing with fresh water before use. For unsound particle, two types of unsound particle, which are those fail to maintain their integrity, those that led to disruptive expansion on freezing or exposure to water. So unsound particles that led to pitting and scaling are shale, clay lumps, wood, and coal. If more than 2.5% of mass aggregate adversely affect strength of concrete. So all of this deleterious material, we want to ensure there is no deleterious material before we mix the concrete. Okay, that is all the parts that you need to know in terms of the properties of aggregates, and also the parts that you need to know the deleterious material that can come with your aggregates. Next is another types of aggregate, what we call as recycled aggregates. Okay, remember the three types of aggregate before this we have discussed, that is come from natural and also comes from your quarry and manufactured, and this one is from recycled aggregates. Okay, this is comprised of crushed graded inorganic particle process, that the material that has been used in the construction and demolition debris. You have an old building on site and we are not using this building, so you hack the building, but you don't have to waste that material to dump. What you can do is use that waste construction material as recycled aggregates. Okay, they are generally from building, road and bridges. It can be produced by two stages. Number one is the crushing of demolished concrete, screening and removal of contaminants such as reinforcement, plastic, and etc. Okay, recycled concrete contain not only the original aggregates but also hydrated cement paste, because most of the building are concrete mix. So when you hack the building, it is in form of hydrated cement paste and also aggregate. Okay, this paste reduces the specific gravity and increases the porosity compared to similar virgin aggregates. Higher porosity of recycled concrete aggregates leads to a higher absorption. And for physical property of recycled aggregates, make them ideally suited for road base and sub base. Use this kind of material for not critical construction, but you can use this recycled aggregate for road base and sub base. And also you can use this recycled aggregate as a filler in your infrastructure work. This is because of their physical property, which means less cement is required, making them suited for sub-base use. So that is all about the aggregates from part 1 up to part 3.